Okay, maybe we can start and then people will join. So welcome everybody to this week's seminars. Our first speaker of today is Angelo Caravano from Paris, and he's going to talk about back reaction and cosmic butterflies, non-perturbative insights into small-scale physics of inflation. I'll send you a reminder when 5 minutes are left.
Okay, thank you so much. So first of all, I would like to thank the organizer of this workshop series for inviting me. It's really a pleasure to show my work here. And I also want to say that if you have questions, um, feel also free to interrupt me during the talk, as long as this is compatible with the format. You can always interrupt me in case you have questions. Today, I'm going to talk about my work on back reaction and non-perturbative nature of inflation. This work is based on the papers that you can see here at the bottom of my slide. So let me start by giving a roadmap of my talk. So at first, I'm going to give you a little bit of an introduction and a motivation. I was gradually moving to the topic. Then I'm gonna tell you the technique. I'm gonna introduce the technique, which is the lattice simulation of inflation, which is gonna be our non-perturbative technique. And then I will discuss some examples where we apply these techniques at the end of the talk. So let me give just one slide introduction to inflation in case some of you is not too familiar with it. So inflation is an accelerated expansion in the early universe. So it's a period where we get an accelerated expansion in terms of the scale factor. It's an acceleration. This is how it's defined. In a standard picture, this expansion is driven by a scalar field, the so-called inflaton field, which basically is a field which is assumed to have a very flat potential, a so-called Laurel potential, so that it moves very, very slowly on the top of this potential. Since it moves very, very slowly, then its energy is constant and it can behave as a cosmological constant approximately, sourcing the accelerated expansion, and in particular exponential expansion. But the most powerful thing about this picture is that it allows us to understand why there are perturbations in our universe from which all the structures in our universe are formed. And these are seen as quantum fluctuations of the inflaton fields that during inflation are stretched to macroscopic and cosmological curvature perturbation imprinted in the sky that then can be seen, for example, as fluctuations in the cosmic microwave background. And I don't want to focus too much on the simplest single field inflation model, where in this minimal model, the only thing that I want to say is that this model is compatible with all the current large-scale observations that we have. It predicts a nearly scale invariant spectrum of these fluctuations. It predicts that they are approximately or very close to Gaussian. Then it predicts that they are very small, and it predicts a slow-roll suppressed tensor to scalar ratio. We haven't observed gravitational waves yet, tensor modes in the early universe, but definitely this is compatible with the slow roll inflation, which predicts a slow roll suppressed with the slow roll parameter epsilon, which basically tells you the flatness of the potential. Now, having introduced the simplest possible inflationary model, let me move to the central question of this talk, and of the work that I will describe here. So the question is about scales in inflation, right? So we know that if inflation happened, inflation, of course, generates fluctuations on the very, very large cosmological scales, and this is why we introduced inflation in the first place. However, if inflation happened, if it generates fluctuations all the way down to much, much smaller scales than the one of the CMB. So let's say that if you are an observer at the end of inflation and you look around, you will see fluctuations on very, very large cosmological scales, but there will also be fluctuations all the way down to at least e to the 40, smaller than the smallest CMB scale. Now, a natural question is, what is the physics of inflation at those scales? At those scales that cannot be probed in any way by large-scale experiments, because these are scales that are so tiny that cannot be probed by for example, by looking at the CMB. And until recently, this question was kind of irrelevant because for this reason we cannot really see it, and the nonlinear gravitational evolution later in the universe kind of washes out these fluctuations. However, recently, thanks to gravitational waves interferometer, now we have an observational windows on the scales that has just been opened. And this is because gravitational waves interferometers, they operate a wavelength that are much, much smaller than the wavelength of the CMB. We talk about the average size of the arm of an interferometer. And in principle, if you get a gravitational wave signal coming from the early universe, you can see it. Now, the only problem is that with current precision, and to really observe something, we need fluctuations on these small scales to be a little bit different than what we observe on the CMB scale. So on the CMB scales, typically these curvature fluctuations that we observe are such that the power spectrum is something like 10 to the minus 9 approximately, which means that average on a fluctuation is going to be something 10 to the minus 5. Now, however, to really be observed with gravitational waves via, for example, scalar-induced gravitational waves at second order in perturbation theory, if you get a primordial power spectrum that is much larger than the one that we observe in the CMB, then you can observe what's happening in the early universe. So without asking if this is natural or not, this is just a fact. If for some reason at small scales during inflation, the small scales of inflation of the inflationary universe, these fluctuations are larger than what we observe on the large scales, and this could be the case. Physics typically tends to separate scales. And this is a question that has attracted a lot of interest in the literature, and people have been trying to think of models that produce this announcement. However, the question that I want to focus for the rest of this talk is, what about potential nonlinear and non-perturbative physics associated with these large fluctuations? So we know that when the power spectrum is like 10 to the minus 9, we can safely trust perturbation theory. But when this power spectrum is larger, it means that we are talking about a fluctuation that on average is something like 10% or 1%. And can we still use the same linear perturbation theory techniques that we use to make the large scale predictions, or is this not enough? And this is a very hot question in the literature in inflationary cosmology right now. This is always phrased as a debate on loops, which basically means that one wants to compute what is the next to leading order in perturbation theory, which if you see this in the analytic calculation, these are typically appearing as loops. And in this question, I want to focus on this talk about the possible nonlinear and non-perturbative physics associated to having large fluctuations generated by inflation. And the technique that I'm going to use to do that is lattice simulation of inflation. So let me introduce this for just a few slides. So just to give you a little bit of an overview, so lattice simulations are a very known tool to study non-perturbative phenomena happening in the universe, and they have been used in the study of the early universe quite a lot, in studying, for example, the reheating phase after inflation or cosmological phase transition. And this is because these phenomena are phenomena that cannot be described perturbatively, because they really require fully non-perturbative and fully nonlinear methods to be understood. Now, my goal in the past few years have been trying to understand whether similar techniques can be used not for reheating, but for inflation itself. So try to develop lattice technique for the inflationary stage of the universe. Recently, I published also a very simple lattice code for single feed inflation that is very simple to use. I will show you the results later, and everything you're going to see in this talk can be easily reproduced with this public code. The results are all available online, so you're welcome to have a look. Now, let me tell you a little bit about the basis of this technique. So lattice simulation basically means that instead of looking at continuous field in continuous space, so here we have the inflaton as a function of space and time, we discretize space-time and we see it as a grid, or also known as lattice, and this is why we call it lattice simulation. It's simply as that. And instead of doing linear perturbation theory, or perturbation theory in general, which means instead of having the inflaton as a sum of a background component plus fluctuations that depend on space, then we don't perform this splitting at all, and this is the crucial point. So we really evolve each value of the inflaton at each of these space-time points in a fully nonlinear way without splitting the inflaton in background plus fluctuations. I will tell you a little bit more details in a second. That's just the basics. Now, the way these techniques work is that the starting point, you start with a box, with a cubic. This is typically a cubic simulation. And you start whenever this cubic box whose size it's up to you is inside the horizon during inflation. So for example, if you're interested in studying the super very large cosmological scales, you can take this to be the whole universe. And then you take it and you trace it back to when it was inside the Hubble horizon during inflation. And similarly, if you want to study interferometer scales, you take a box of that size and you trace it back to when it was inside the horizon during inflation. And this is the starting point of the simulation. And this is the point where the fluctuations are initiated on this box as the quantum fluctuations are initiated. Now, this is where the first, let's say, the first approximation comes into play, because of course we cannot, deterministically assign values to quantum fluctuations because they're quantum. And so we make some approximation, and the way we do this is, and this is really standard in all, for example, even reheating simulations and all types of simulations of this kind, is that one takes a stochastic point of view. One makes basically a realization. One can make realizations of the field that really look like the quantum noise, have the same power spectrum, but they're effectively just stochastic realization of it, and they are supposed to mimic the quantum noise. Then once these initial conditions are set, what this code does is that you solve numerically for each of these points. You solve for all of them the full equation for the inflaton with all the gradients and the potential, which has all the nonlinearities in it. And then together with it, it solves the Friedman equation for the scale factor, where rho and p are the mean energy, density, and pressure contained in this universe. Now, this is where the second approximation comes into play. Here we're assuming an unperturbed metric. So we work on a Friedman-Lemaitre-Robinson-Walker metric, which is dynamical and evolves depending on what's inside the universe, but we don't model the evolution of the metric perturbations. Now, typically, if you just think of single field inflation, you can safely put to zero all the spatial components of the metric, of the scalar perturbations associated to scalar perturbations. And this is simply a choice of gauge. We are working in the so-called spatially flat gauge, so that the scalar degree of freedom in the metric is in the field itself. And this can always be done. However, there's always the delta G 0 mu component of the metric. And typically, these are the non-dynamical components in GR. And these are typically during inflation, these are slow roll suppressed. And actually, this neglecting setting these components to zero is exact in a well-defined limit, which is called the decoupling limit of gravity, in which whatever field dynamics you have is decoupled by the gravitational interactions. This is going to be the limit where I'm going to be for the rest of this talk. So I'm going to choose models so that I know that I'm very close to this limit. But in principle, this can be relaxed. One can put linear metric evolution inside this code as long as this epsilon is small, and one can model this. But as far as the rest of this talk is concerned, I will just neglect metric perturbations in the temporal component of the metric perturbation. While I stress again that this one we set to zero, but they're effectively there in the scalar field. Okay, now the way then it works is that you take these initial conditions and you evolve until this box has become super horizon. So where it has expanded, we're working in comoving coordinates, so that actually the box is not expanding, but it's space itself that is shrinking. So the horizon is going to be smaller at the end of the simulation, and we're going to end up with a super horizon box. Now, we don't need to go until the end of inflation typically to then extract the observables, because typically the super horizon dynamics of physical quantities is frozen by causality during inflation. Now, just before moving on to the results, I want to stress what are the key points of this technique. So the advantage is that this is a fully non-perturbative technique, meaning that in this evolution, we never introduce, except from the initial conditions, we never introduce a notion of background. So when we evolve the field is all together, and there is no, background field plus fluctuations. The field is together. And that there are some assumptions that we need to be careful, like that we neglect purely gravitational interactions. And also that this is a semi-classical approach. So this is a classical simulation with some semi-classical method to generate the initial conditions, which means that if we have some purely quantum phenomenon, like for example, quantum tunneling or interference, on some really purely quantum phenomenon, we're not gonna see it in this simulation. Okay, now before going to the results, actually I have a movie that I recently made. I'm gonna show you here the movie of inflation made with these simulations. Here you see, Here you see this sphere is more or less showing the size of the horizon during inflation. And now soon you will see what happens to a 2D slice. This is a color map. This is a surface plot, and you see this is a 2D slice of what's happening during inflation. So you'll see that you have these quantum fluctuations at the beginning, and this is an actual movie made out of the simulation. You have these quantum fluctuations at the beginning, they're super large on super horizon scales, then the horizon shrinks and this box becomes larger and larger than the horizon. These fluctuations will freeze down to the scale invariant, nearly scale invariant power spectrum of inflationary fluctuations. And this is how more or less a 2D, two-dimensional slice of the inflationary universe looks like. And it's already interesting to see what is and how inflation looks like in real space. I find it already quite nice as an outcome of this simulation to visualize inflation.
Sorry, can I just
Yeah,
ask, so how much time does it take for these kind of simulations?
it highly depends on the resolution that you want to have and the kind of phenomena that you want to simulate. Because depending on how many points you have in your lattice, this can change quite drastically. For the typical simulation I will show during this during this talk, we typically have 500 cube boxes, which means we have 500 cube points. And for this kind of simulations, it approximately take 10 hours on a normal computer with a basic parallelization, but this is a simple parallelization on a single CPU machine. So the average time is on the order of 10 hours. You can make it faster if you parallelize it on more machines. But for this code, this public code, it takes more or less 10 hours to run one very big simulation. So 512 cube is relatively large. Now, let me move now to the physics, and I will show you some examples of this technique. So I will first focus on an oscillatory potential, some sort of monodromy potential. I will introduce it in a moment. I also studied ultra-slow roll inflation. I'm not sure I have the time to go into the details of that during this talk, but let me start by giving the first example first. Now, let's come back to the original question of the talk, and let's ask, what is the physics of inflation at scales much smaller than the CMB? Now, in order to try to understand what kind of things these simulations can give us on this question, I'm going to consider a toy model. This toy model is basically a way where we put a small scale modification of the inflationary potential. We basically assume, just as an exercise and to try to understand what's going on, that the potential is the sum of the usual slow roll potential plus some modification. And this modification, we have it on small scales in a way that it's away from the dynamics that pertains the CMB modes. So here there's a window function here that localizes this oscillation. This is just a window function that puts this oscillation where we want here. And then I consider an oscillation. Now here I'm saying this is a toy model, but actually there are these monodromy potential are really motivated from the UV perspective, from axions having this sort of potentials with oscillation. So one can make concrete models with this feature. Like one can think of two models where at some point a second field takes in and have the oscillation. But here I'm just thinking of it as a very simple parameterization. There are a few parameters, this cosine potential and a width function and an amplitude for the oscillation, just to keep it simple. Now, why the oscillation? The oscillation is a very efficient way of creating particles. So because there is the oscillation, there's a parametric resonance phenomenon. Basically, because there is this oscillation frequency of the background, there are going to be some modes that resonate with this frequency. This is basically exactly the same of reheating, but the field, instead of oscillating on the bottom of the potential, it oscillates on the potential. But the equations are exactly the same for the resonance itself. And because of this oscillation, then there's going to be an exponential growth of the perturbations, which then will make this model observable. And I'm going to consider three types of oscillations here for the simulation. I'm going to take three cases. I don't give you really the parameters of the oscillation and of the frequency. You can find them in the paper. It's not really important. What I want to show is that I'm going to just pick three models. The first one is this green here. The second one, I basically take the same amplitude, but I take the frequency to be twice the frequency, you see, of the oscillation. And then the third, I'm going to take the same of the first case, but I'm going to slightly decrease the amplitude. You see here that slightly increase the amplitude of the oscillation. You'll see here that the blue has a slightly higher oscillation amplitude. And now let's see what linear perturbation theory, what standard methods tell you about this model. So this linear prediction, which just means, solving the Mukhanov-Sasaki equation numerically, will tell you that with this potential, you get this power spectrum here on the right. You basically have the usual scale invariant power spectrum that on top of it, there is a localized excitation. This excitation is caused precisely by this feature. And in these three cases, you will see that we have kind of different situations. So in the first case, the power spectrum is enhanced and the peak is around 10 to the minus 5 of the power spectrum. And in the other two cases, the power spectrum peaks around 10 to the minus 2, which is the interesting range for primordial black hole formation. Now, actually, the real reason why we choose exactly these three models is because some people have performed a loop calculation of this model here. And they shown that if you try to calculate the one loop correction to this power spectrum, in case one, it seems okay. It seems that this loop correction is much suppressed with respect to this to the three-level linear component. But in cases 2 and 3, this is not the case. The loop correction starts to be of similar size. And again, it's a very subtle issue to estimate these loop corrections. There's a huge debate in the literature. But in this case, 2 and 3, it seems to be that these loop corrections might create some problem to perturbativity of this system. And this is why actually we decided to pick this particular model to make the simulation. Okay, so now I introduce the model and let's go to the simulation itself. Again, if there are any questions before I move to the simulation results, please interrupt me. And I will slowly start by the first case. So the first case has a relatively small power spectrum, so we don't expect deviations from perturbation theory to be so large. And this is indeed what happens. And this is a case just to try to familiarize ourselves with this kind of simulation and what the simulation shows. Now, on the left, I will show you, there's going to be no plot, just a movie. On the left, this is a two-dimensional snapshot of the inflaton field evolving with time. N is the number of E-fold. And on the right, you see the distribution of the values of the inflaton on this universe. So this is basically a PDF, is a histogram, is a probability distribution function, is a histogram of values of the inflaton across this box. And you will see that the inflaton is a sharply peaked distribution with one main background value as the usual picture, and it's consistent with the usual picture. And then, this field moves on the oscillatory potential here. You will see here a plot, also the potential on top of it, and it goes up and down, and there are some very interesting feature in real space imprinted in this field, and which are already something very non-trivial, because this model has some complicated non-Gaussianity that is very difficult to understand. And here we can really see in real space what this non-Gaussianity is imprinted in this model, and how does this feature affect the statistics. It's already interesting on its own, but everything seems to be more or less consistent with perturbation theory. Now, let's move to the second case, which is similar to the first case, but there is some oscillation which has double. There are more peaks, basically. There are many more peaks there are twice as more peaks in the same region of the potential. And now, again, I want to stress that this was a model where perturbation theory was telling you that everything is fine, and the power spectrum will be 10 to the minus 2, which basically, just coming back to the potential, will tell you that according to linear perturbation theory, this feature they are small enough so that the inflaton is able to go up and down this feature and go down to the right part of the potential. This is what linear perturbation theory would tell you, and the power spectrum is going to be 10 to the minus 2. However, when we run the simulation, we find something a bit different. So we observe that instead of moving on the next region of the potential as the linear theory would tell you, the inflaton is actually completely stuck into this oscillation. So what linear perturbation theory was telling you is very, very different from what's going on. And we start understanding maybe a little bit why we decided to call this inflationary butterfly effect. I will show it in a minute. So the reason is that here we're talking about what's happening here is that basically, because of this small scale feature in the potential, the whole universe here is stuck inside this potential. So in this particular universe, inflation does not even end because it's completely stuck in this potential. You will see here that red and blue are two different regions, slightly different energy density of these two minima where the system is trapped. But this system will never become our universe. And this is really because of this small scale physics that it's happening. So it's the small scale physics that it's really modifying the full trajectory of the universe, and in a way that it's, because of the system is non-linear, in a way that it's highly complicated. We will come back to it in a second, of the motivations about why we decided to call it this way. So in this model, the universe is stuck. And this is a surprise. There was no way in perturbation theory to try to understand how this was happening. Now, let me give a motivation of why this trapping happens. And this has to do with energy. Now, if we look at the perturbative case here, at the first case that we looked at, we will see that if we look at all the three different energy, the potential, the kinetic, and the gradient energy in the inflaton field, the potential will remain the dominant component, and that's fine. That's basically tell you that our neglecting method perturbation is fine. Then there's going to be the kinetic energy of the inflaton and the gradient energy. And the gradient and the kinetic, except at the beginning, they're kind of separated. However, in this case where the dynamics is very different from perturbation theory, what happens is that actually the gradients grow so much that intersects the kinetic energy. So what does this mean? This means that the reason why perturbation theory was failing in describing what's going on in this system, it's that according to perturbation theory, you can create gradients out of nowhere. You can just produce them indefinitely. But in reality, in the full nonlinear picture, whenever you're producing gradients, this energy needs to come from somewhere else. And this energy typically comes from the kinetic in this case. So in this case, the gradients are growing and they're sucking up kinetic energy, which then makes the system stuck in this system. While if you had no perturbations at all, if you started with, instead of this tiny distribution, you just started with one background value, there would not be such a trapping. It's really the perturbations themselves, these tiny quantum fluctuations, that are affecting the overall dynamics. Now let's look now at a case where there are in the intermediate case, so where basically the amplitude is just a bit higher than the first case, and this is a sort of an interesting mixed situation that can happen, where you will see that instead of being fully trapped, or instead of escaping completely, the universe splits into. There's some regions, there's parts of the universe that are able to escape this potential, and some parts of the universe that are trapped in this potential. So the notion of background is lost as a global quantity, and you have, depending on where you are, you're going to be in a different background, in a different universe. And now, the first naive thought that I had about this is that, okay, now this is going to be the situation, that's where the simulation ends. But if we try to extrapolate what's going to happen after inflation, is that at the end of inflation, this region is going to fall down the minimum of the potential, and these red ones are going to stay there forever in the sitter. So they're going to take over the whole universe, and this model is also ruled out. However, this thinking is a little bit naive. And in order to understand what's really happening at the end of inflation in this model, and again, this is not something that we study with the simulation, this is something that then we try to understand what's going to happen at the end of inflation in this kind of models, is that in the end, what's going to happen at the end of inflation is that the blue regions are going to end up in the true vacuum, and they're going to reheat, while these red regions are going to inflate forever. However, these are regions that are trapped in a false vacuum, so they have a much high energy than the true vacuum, which means that there's nothing really more that can happen, that these regions, the red regions, should collapse into black holes at the end of inflation. Now, how can the two things be true at the same time? These things expand forever because they are de Sitter regions, and at the same time they're going to collapse into black holes. And these things might sound incompatible, but actually they are compatible. And this is because GR is complicated. General relativity is complicated. What we're going to have is that, each of these regions on the inside, if you're an observer inside these regions, you are going to see inflation, because these regions are large enough for you to not see what's outside, and you just see inflation. But if you're outside, you will see a bounded object with a very high energy density that at some point are going to collapse. This false vacuum trapping phenomenon be studied in the literature. So we just had to understand that our situation was analogous to false vacuum trapping, but all these detailed dynamics of false vacuum trapping and what happens has been studied already, so we could rely on these results. And what we can do, relying on the results existing in the literature, is we can try to estimate how many of these black holes, which are primordial black holes, are formed in the early universe. And these primordial black holes, I want to stress, that are really completely different than what you typically get from a collapse of a high density region. They're really just a region of space-time that is completely detached from the universe, and it's a whole universe on its own. And we estimated how much this mass fraction in PBH at the end, at the time of their formation, we estimated analytically at first order. We estimated at first order from the simulation, using this simple relation that these people estimated, which is a first order approximation of trying to understand how many of these objects you're going to have. And we also experienced how this will depend on the resolution and on the coupling and amplitude of our simulation, sorry, or the physical parameters on this model. Now, let me motivate for 1 second of why we call this inflationary butterfly effect. So the original butterfly effect was about us asking how much, it was, in the context of the development of the chaotic of chaotic system. And the original question was, can the flap of a butterfly wings in Brazil set off a tornado in Texas? And this was a provocative way to stress how much these nonlinear systems, which were convective systems that we were studying at the time, describing the atmosphere, were highly unpredictable in the sense that we're highly sensitive to all the details and to of the system and to the initial conditions. And here we are building this analogy. It's just an analogy. Of course, it's very different, but it's an analogy that can help us a little bit in picturing what's going on. And the equivalent here is, can these tiny, small-scale quantum fluctuations present on sub-horizon scale and also on much, much smaller scales than the CMB completely affect the dynamics of the entire universe? So this link with a chaotic system is quite relevant in this case, as we have seen. Now, but if you want to be more pragmatical, let's say that the main lesson here is that if you have a system that predicts an inflationary model that predicts a power spectrum of 10 to the minus 2, then it could be, as we have shown in our case, that perturbation theory is completely broken. In some cases, like the ones that we have shown, you don't only get corrections to perturbation theory, you get that the whole perturbative picture is completely broken, and you need to resort to this technique to understand what is going on. So how does this link with loop calculations? We compared our result with the loop calculation that these people did and found that some of the effects were well captured by this loop calculation. So we do the loop calculation in the perturbative case, where we can trust perturbation theory, we understand that everything is okay. Then we can compare what we see with the loop calculation, and we see that the IR tail here, in blue we have the simulation result, and in red we have the one loop corrected power spectrum, and you will see that on the IR we get a better agreement than just the 3-level calculation. There are also other effects that seem to point at things beyond one loop, or other corrections, maybe due to the classical nature of the simulation, we don't know, but this is still under investigation. Now, I will not talk about this ultra-slow roll inflation. I'll just briefly mention that it's another well-known mechanism to enhance fluctuations. Is an inflection point in the potential. And because we wanted to understand how general are these conclusions, we also studied in these models. And we also understood that there are important effects beyond perturbation theory, beyond linear perturbation theory, when trying to describe these systems. And you're welcome to have a look at our work. Here, I don't have the time to go into the details of this. I think that at this point, in the interest of time, I can just straight move to the conclusion, so I can leave some, so I can answer to some of your questions, and I don't want to make this too long. So let me give a brief summary of what I've been talking about in the past half an hour. So the summary is that we're developing these lattice simulations of inflation, and these are a new technique that allows to study what happens during inflation. And it is a technique that we're making publicly available, and it's ever expanding. And we can use this technique, and we've been showing that you can finally know what happens when perturbation theory is not reliable during inflation. And this is extremely relevant for probing the small-scale physics of inflation using gravitational waves. We haven't really calculated the gravitational wave signal, but we have shown that in models that are interesting for gravitational waves astronomy, these simulations are essential. But there are also other applications beyond the small-scale physics of inflation. For example, understanding models where this back reaction is important for other reasons, like, for example, axion inflation. Now, what's next? Next step that we're working on is to develop techniques to actually, now we just studied, the dynamics in the system. And we studied how much perturbation theory is reliable, but we haven't calculated any actual observables out of this quantity beyond this primordial black hole abundance that I showed before. For example, we haven't calculated the gravitational wave spectrum, and this is what we're planning to do next. So trying to use this simulation to actually compute the observable